Okay, next we will discuss about exact differential equations. And before discussing the exact differential equations, let us first talk about the exact differentials. Uh, there are some types of differential equation which looks like x dy plus y dx equal to 0, and we can write the left hand side as uh, d of xy. This the left hand side of this equation, this is a differential equation, and the left hand side of this differential equation can be written as a differential of some function xy. If if we write in this way, then this differential is said to be exact differentials. It is called exact differentials. So if we write it in this way, there is the left hand side if is written as a differential of some function, then this differential equation is said to be a exact differential equation. Now let us explain this. There are some functions or family of curves. Suppose if which is a function of x and y, both x and y, which is equal to c, a constant. This is the number of this different equation. Now, if f is continuous and has first order partial derivatives in some region in the xy plane, then we can generate a first order differential equation. So if xy is continuous and has continuous first order partial derivatives, then you can generate first order differential equation from this equation 1. So the function is a constant. So the differential of this function d, that is a total differential of this function, which is equal to 0. Now so if dm is the total differential of this function, we can write the total differential as partial derivative of f with respect to x when y remains constant into dx plus partial derivative of f with respect to y when x remains constant into dy. So this is equal to 0. So this becomes the differential equation, first order differential equation. So what I have said, that if there are some familiar curves or functions, if f equal to c, and if this function is continuous and has continuous first order partial derivative, then we can generate a first order differential equation from this equation 1, which is this, that is del f del x into dx plus del f del y into dy is equal to 0, which is equation 2. Now this partial derivative, which is also a can also be a function of x and y, both x and y function. So del f del s is also a function of x and y, and this del f del is also a function of x and y. So if the differential equation is this in this form, then we can convert this left hand side into a differential of some function, this. So this is basically in reverse, we can say that is d of f equal to 0. So that is the differential of that function f, which is equal to 0. Now let us give an example. Suppose the function is f xy equal to x square minus 5xy plus y cube equal to c. So the function is this. Actually, this is the solution. This is the solution of the differential equation. Left hand side has to be exact, so that the differential equation obtaining from this solution would be an exact differential equation. So now we will first calculate the partial derivative of f with respect to x, that is 2x minus 5y. So del f del x means differentiating f with respect to x when y remains constant, that is 2x minus 5y, and calculating the partial derivative of f with respect to y when x remains constant, that is del f del y is equal to minus 5x plus 3y square. So these are the partial derivatives, and we know that from this equation 1 we see from the equation 2. Now putting this values of del f del x and del f del y into the equation 2, and we get 2x minus 5y into dx plus this is 3y square minus 5x into dy equal to 0. So you see here that the del f del x, which is also a function x1, as I have written here, and this del f del y is also a function xy. So the differential equation we get, this is said to be a exact differential equation, because we can write it in this way, that is d of x square minus 5xy plus y cube equal to 0, and from this we can come to this solution. So this can be written as m function of y dx plus n function of xy into dy equal to 0. So we can define a exact differential equation in this way, that if the differential equation has the form that is mxy dx plus n of xy dy equal to 0, if this part, that is mxy dx plus n of xy dy is written as a differential of some function, Now we will discuss about the criteria for an differential equation to be exact. Criteria for an exact differential equation. Suppose f of xy is continuous, and its first order partial derivative is also continuous, in R in xy plane. So then from the equality of the mixed second order partial derivatives, then from the equality of the mixed uh, second order partial derivative, write del to f del x del y del to f del y del x. So what I said, that if f is continuous and its first order partial derivative is also continuous in some region or in xy plane, then from the equality of the mixed second order partial derivative, we can write del to f del x del y equal to del to f del x del x. So here del to f del x del y is actually the partial derivative of del f del y with respect to x. So this is written as partial derivative of del f del y with respect to x, which is, and this is actually partial derivative of del f del x with respect to y. Now let us let me show you some example. Suppose the function is f of x y equal to x square minus 5xy plus y cube, and so here del f del x is 2x minus 5y. Next, calculating del to f del y del x, that is equal to minus 5. Similarly, calculating del f del y is equal to minus 5x plus 3y square, that is del 2f del x del y equal to minus 1. So they are equal. This partial derivative will be equal only when this partial order derivative exists and it is continuous. When it is continuous, that is if fxy and fyx. Fxy, that is the del 2f del x del y, and f of x del 2f del y del x. When this partial second order partial order derivative continuous, and so then we can write this, that is a mixed partial derivatives are equal, this equation. So this is the example. You can see they are equal. Now give this equation number 3. So now we know that the differential equation mxy dx plus mxy dy equal to 0. Suppose we have to prove that this is an exact differential equation. Now let us first consider that this part, the left hand side, is exact differential. So we have to find out the condition, that is the criteria for an exact differential. So so if it is an exact differential, then it can be written as, so there exists a function in dx plus n xy dy which will be differential of some function t of x y. So we can write it as del f del x plus del f del y dy. So from the equation we equating the coefficient of dx and dy. So we can write m x y is equal to del f del x and n x y equal to del f del y. So we got this, that is m, which is there is the partial derivative of f with respect to x, and n, which is equal to the partial derivative of f with respect to y. So now from equation 2, from equation 3, we can write from equation 3 is the equation that is correct. So m equal to del f del x. So this is the a, this is the m, and this is m. So we write del n del x equal to del n del y. So we got the condition, that is del n del x and del n del y. So the condition for an exact differential that is del m del y equal to del n del x. So this comes from the mixed first order partial derivative. No, so second order partial derivative, that is del 2f del x del y equal to del 2f del y del x. So that this condition is satisfied when only this partial order derivatives are continuous. When the partial order derivatives are continuous, then you can say the mixed partial second order derivatives are equal. So so we can say that the first order derivative, first order partial derivative of m and n is also continuous in that interval. Continuous. So we can define the criteria as so the criteria is can write here if m xy and n xy is continuous and have continuous first order partial derivatives in a region R in xy plane, then n xy dx plus n xy dy is differential. del n del x. So the criteria is if m and n is continuous and have continuous first order partial derivatives in a region R in xy plane, then m dx plus n dy is an exact differential if del m by del y equal to del m by del x. So we can say that the differential equation of the form m dx n dy, sorry, m of x y dx plus m of x y dy equal to 0 is said to be an exact differential equation when this term is an exact differential. That is when this condition is satisfied, that is del m del y equal to del n del x. Suppose the differential equation is 2xy dx plus x square minus 1 into dy equal to 0. So here this is the m and this is the n. So let me first check the condition for an exact differential, that is del del y, that is equal to 2x, and del n del x is also equal to 2x. So the condition is satisfied. So we can say that this is an exact differential equation. Now we have to solve this. So for solving, we know that m equal to del f del x, and this is equal to 2xy. So now first, then integrating this function, we can get the function as xy equal to x square y plus constant. Now so here we are integrating this equation with respect to x and y remaining constant. So the constant is said to be a function of y. So this is g of y. This is a function. This is a constant. So now let us give this as equation a, and an, which is del f del y, that is equal to x square minus 1 square minus 1. Now differentiating the equation a with respect to y, we get del f del y equal to x square plus g of y. So now comparing these two equations, we can calculate the value of the constant, and that is here g of y. So g of y is equal to minus 1. So we get the function from equation a, that is f of x y equal to s square y no, sorry. So this is when differentiating with respect to y, it would be g dash y, a dash y. So g of y equal to minus y. So the function is x y equal to x square y minus y. So first we consider that the function is the solution of the solution for the exact differential equation is a for x y equal to c. This is the solution. So the solution is equal to constant. So this is the solution of this exact differential equation. Okay, next we will discuss about the existence of a unique solution of a differential equation. We saw that some of the initial value problems have more than one solution, and so you see here this initial value problem, that is dy dx plus x y to the power half and y is equal to 0 at x equal to 0. Y equal to 0 at x equal to 0. So this differential equation has two solutions, which is y equal to 0, which is the singular solution, y equal to 0, which is the singular solution, and another is y equal to x to the power 4 by 16. So both the solution passes through this origin, that is 0, 0. So here we cannot define any unique solution for this differential equation, and so the this solution y equal to x to the power 4 by 16 is represented by this curve, and y equal to 0 is represented by this black solid line, which is y equal to 0. So both the curve both the solution which is passing through this point. So the solution of this differential equation or this initial value problem is not defined uniquely. So so to define the unique solution of a initial value problem, we will discuss a theorem about it. So this is the theorem for the existence of a unique solution of a first order differential equation. It is written here that let R be a rectangular region in the xy plane defined by in the x domain a to b and y domain c to d. So here between a to b and c to d there is a rectangular region R, and which contains the point x0 y0 in its interior. So this is the point x0 y0 in the interior of this region. Now in this region R, if f and del f del y are continuous, then there exists an interval. This is the interval centered at x0 y0, this point. Unique solution yx is defined on this interval, satisfying the initial value problem. So let me repeat that if R is a rectangular region and centered at the point x0 y0 defined by this closed interval a to b and c to d, and if f of x, if the function f and del f del y are continuous on R, then we can define an interval I on this region, and on that interval the differential equation or the initial value problem has a unique solution. So now let us come to the example, that is the dy dx equal to xy to the power half. So here you see that this right hand side of this differential equation is actually the function which is f of x comma y. Now this function is continuous for all values of y, that is y greater than equal to 0. This function is continuous, but del f del y, you see that there is continuous only for y greater than 0. So it shows that they are continuous in the upper half plane defined by y greater than 0. So for y greater than 0, there exists only one solution, which is y equal to x to the power 4 by 16. You saw that the solution, the differential equation has two solutions. There's one is y equal to x to the power 4 by 16, and another is the y equal to 0. So y equal to 0 is not possible because here del f del y at this point is not continuous. So only this solution is possible. So the solution is which is y equal to x to the power 4 by 16. So from this condition, and that is from this theorem, and we can identify the unique solution of a differential equation.